next chapter is the congruence, power, and Euler's formula. So okay, so the Fermat's little theorem, what we saw is that if P is a prime, so just recalling the Fermat's theorem, so P is a prime and P does not divide it, so this will imply that a to the power of P minus 1 is congruent to 1 mod P. So this is the Fermat's little theorem.
Right,
But the
P
question is,
prime,
yes,
P no divides A. The GC is the PGCD, PA1, right? It's the same thing.
yes, P does not divide, that will same.
Yeah.
So yes, so the thing is, the natural question that comes into mind is, so what will happen if P is a composite number, right? So if we replace P by a composite number, so whether it still holds or not. So actually it is not true. So let us see. So if we replace P by a composite number, then what you have is, let us see an example. So 5 power 5 is congruent to how much? So if I take modulo 6, so P here I'm replacing by the composite number 6 and I'm taking 5 power 5. So you can check that it is 5. So it is no longer 1. And similarly, one more example, 2 power 4 or 2 power 8 is congruent to 4 mod 9. So here 9 is again composite. So this formula is not true when P is a composite number, right? So the natural question is asked, we can ask is, that whether there is some power such that depending upon that depends upon n, such that a power, suppose this one I have to figure out, so what will be here, so it is congruent to 1 mod m. So can we get something that only depends upon n m such that when I raise a to that power, it becomes 1 mod m. So that is a natural question, right? So here m, we have no restriction, m can be prime, m can be composite, it can work for any m, right?
Okay.
So now so let us see what is the condition upon a and m. So the thing is, the GCD of a and m, so let us see what has happened. So does it do we force or do we need that this GCD also need to be 1? So that we have to check. So suppose for some power k, a power k is congruent to 1 mod m, right, for some k. So then this implies that m divides a power k minus 1, right?
Yep.
So this implies a power k minus 1 is equals to m times y for some integer y. So this implies a power k is equal to my plus 1, right? So from here, can we say anything about GCD of A and M? What can we say about GCD?
So-
Whether it has to be 1 or can it be greater than 1?
I mean, just based on that, we cannot say anything.
No, actually, you can say. So, for example, suppose we assume that D is the GCD of A and M, right? So, this implies that D divides A as well as D divides M, right?
Mm-hmm.
So, from here, I have 1 equals to A power K minus My, right?
Right.
So, since D divides A and D divides M, so D must divide this quantity, right? So D divides A power K minus My, right? Because A power K and M both are divisible by D, right?
Mm-hmm.
So this will implies that this will imply that D must divide 1, right? So this forces D to be equal to 1. Other than that, we have no option,
Right.
right? So if we have to, so you suppose there exists some K for which A power K is congruent to 1 mod M. So that will only work if the GCD of A and M is 1. So that first condition we need. So GCD of A and M has to be 1, right?
Okay.
Okay. So now, so from this condition, what we understand it, so you have to look into the set of numbers that are relatively prime to M, right? So we look at the following set. So look into the set of numbers A such that A lies between 1 and M, and the GCD of A and M is 1. So this is the condition needed, right?
That is just the last demonstration, right?
Yes, so that is what we observed till now. That so this will if we have to find some value of k that only depends upon m, such that a power k is 1. So first condition, it need to satisfy that a must be co-prime with m. So the GCD of a and m should be 1, right?
Mm-hmm.
So let us see for some small values of m, what is the list of these numbers where this is co-prime. So suppose m we have here, and on the other hand we have this collection a such that 1 less than equals to a less than equals to m, and GCD of a m equal to 1. So suppose m is 1, then we have only 1, right? This set is only 1, right?
Mm-hmm.
So suppose we have 2, so then this set will be, this is
1,
still 1,
2.
right? Already. Fine.
But it says less than equal
Right, less than equals to m, and the GCD
n.
has to be 1. So 2
Then
with 2 GCD is 2, right? So 2 cannot be in the set, right?
and GCD of A and M must be 1. Yes.
Right. So now if I take 3, then this set will be 1 comma 2, right? Because both are less than equal to m, and the GCD with 3 is 1, right?
Right. Yep.
So for 4 it will be 1 and 3, because 2 we cannot put because 2 has GCD greater than 1, right?
Mm-hmm.
For 5, what will be the set?
1, 2, 3, and 4.
Right, all of them will be there. But for 6 I can have only 1 and 5, right?
1
Because
and 1 and 5. Right.
2, 3 and 4 we cannot have. So 7, again all of them will work up to 6. 1, 2, 3, 4,
Yeah.
5, 6. Right. So okay, well, let us see one more, then you can understand the pattern. So for 8, what will be the set?
All the non-pair 1, 3, 7.
Yes,
5.
1, 3, 5, and 7. Right. So what we observe is, so this is so whenever a number is a prime, so for example, if we see this number, so whenever a number is prime, all the numbers before that it is there in the set. Similarly, for 5 it will work, and similarly for 7 it works. So when m is a prime, all the numbers that is before that up to m minus 1, so that are co-prime to that number, right?
Mhm.
Right. So this set, the number of elements in the set, we are defining this one as a special quantity. So the number of integers between 1 and m that are relatively prime to m is an is denoted by phi of m. So this is the cardinality. So this denote cardinality, or the number of elements. A says that A lies between 1 and m, and GCD of AM is 1. And this function, the function phi, is called the Euler's phi function.
The Euler's
Euler's phi function, PHI, phi function.
So an integer between 1 and n that such that that integer
Yes,
GCD with n is 1.
right. So this is a set. This is a set, and we are taking this is the cardinality. Cardinality means the number of elements in that set. So that will be a
Yeah,
number, right? So that is denoted by phi of m.
right.
Okay. So this is the name for the Euler's phi function. So now from this table, what you have obtained. So now if I want to calculate the phi of m, so here phi of m from this table you can easily calculate. So this will be 1.
1,
This is
1, 2,
1.
2.
Right. Next one is 4. Then again 2, 6, 4. Right. So this is the phi function.
2, 2, 4, 7, yeah.
Right. So one observation is, so note that if p is a prime number, then every integer is relatively prime to every integer strictly less than p is relatively prime to p. That we already know. Right. So what I have is, so phi of p, whenever p is a prime, that is p minus 1. Right.
Mm-hmm.
Right.
Right. Only when p is a prime. Other than
Yes.
that, we don't know.
Yes. When p is a prime, I can say that it is p minus 1. This phi of p is p minus 1.
Okay.
Okay. Okay. So now let us see that the first question that we asked, that when what number can we find here that is depending upon m such that a is congruent to 1 mod m. So let us try to find that for a number. So suppose here A is 7 we are choosing. Suppose A equals to 7 we are choosing, and M equals to 10 we are choosing. So here 10 is not a prime, so we are choosing a composite number. So we are trying to find a power of 7. 7 power what? That is congruent to 1 mod 10. Right. So first of all, this condition is satisfied, that GCD of 10 and 7, this is 1. So we can actually find a power. But now let us see what will happen. Right?
Okay.
Okay. So now we take all the numbers that are relatively prime to 10 first. So the numbers that are relatively prime to 10 are, what will be the numbers? What is the set?
Numbers that are related prime to 10 would be 3,
Yes. 1 is there.
7, 1, 3,
1, 3,
7,
7. Yes.
9.
9. Right. So these are the numbers, right? Now, so if I multiply each of them, each of the numbers by 7, so then what I get is, so multiply by 7, and then we get the following congruence. So first time multiplying by 7 with 1, so that is congruent to 7 mod 10, right? Then if I take 7 times 3, that is congruent to 1 mod 10, because 21, that is 1 mod 10. Then 7.7 is 49, so that is 9 mod 10. And 7.9 is 63, that is 3 mod 10. Right?
You're doing so. So the set 1379, you're multiplying by 7. Why?
Yes. So we are multiplying by 7 and taking modulo 10 to show that the resulting numbers also lie within this set only. So if you see the resulting numbers after taking mod, that still lies into this following set. So that is the observation I wanted to show. That if I multiply each number by 7 and take modulo 10, then after all the numbers, resulting number lies within this set only.
Okay.
Right? So up to this is fine, right?
Yeah.
Right. So now if I multiply all the congruences, so there are 4 congruences. So if I multiply all of them, then what will happen is, so if we multiply them together, we have, so 7.1 times 7 3s, then 7 times 7, and 7 times 9. So that is congruent to 1 3 7 9 mod 10, right? So now here also you can see that these numbers 1 3 7 9 is there. So if I combine them together, what I have is 7 power 4 times 1379 is congruent to 1379, right? So you can so this whole thing is co-prime with 10, so you can cancel them. So I get 7 power 4 is congruent to 1 mod 10, right? So actually what we wanted to find, that we found, right? So we found a power such that 7 power 4 is congruent to 1 mod 10, right?
Mhm.
But the thing is, our aim was to find this as a function of 10, right? So what will be that? Can you tell?
Sorry, you repeat that
The thing
question?
is, our main question or our main aim was to find here some power that should be related to this m, right? This is m is 10 here. I want to relate with it m, right? This power.
So the power, what is the relation with the mod 10?
Right, right, 10.
With 10.
So here you can see that the relatively number of elements that are relatively prime to 10 are the four quantities, right?
Is the cardinal.
Right. So that is the set, that is the thing we defined in the last thing, right? So that is the phi of m, right? So phi of m is the number of elements that are less than m and the coprime. So this 4 is nothing but phi of 10.
510, which is the set of numbers that are between 1 to 10 that are
GCD,
coprime with 10.
right. So that is nothing but this set, right?
Mhm.
So this 4, this exponent, this 4, it is nothing but this phi of 10. Right? So what we
Mhm.
got actually is that 7 power phi of 10 is congruent to 1 mod 10. So I got a exponent of a in terms of m such that a power phi of m is congruent to 1 mod m, right?
Right. Mhm.
So that is actually that gives our the a formula or a theorem that is called the Euler's theorem.
Yeah, I see. I see. I see.
So this is called the Euler's formula. So the statement is if GCD of a and m is 1, so that is needed, then a power phi of m is congruent to 1 mod m. So here we have no condition or no restriction of where m is prime or m is composite. That we have no restriction.
The theorem is GCD of A and M. Right.
Okay.
Mhm.
So here you can see that this is actually an extension of the Fermat-Seidel theorem, because if I have m to be prime, suppose m is equal to some prime p, then this phi of p, I know it is p minus 1, right?
Right.
So that is actually matching with our Fermat-Seidel theorem, right?
If n is, what did you say, if n is prime,
Yes, yes. So the thing is, if I
then
take the special
phi
case,
n would be n minus 1, right?
right? So then it will be p
Mhm.
minus 1, right? So then this is actually phi of m because m is p. So then it matches with our the Fermat-Seidel theorem. So this is 1 mod,
I see.
right? So this is our Fermat-Seidel theorem.
So the Euler's, how do you say that?
Euler's
Euler's.
formula, right? Yes, anything.
Euler's.
Yes, Euler's formula is the extension of the Fermat-Seidel theorem.
It's a generalization, right?
Yes.
Okay.
Okay. So now let us see how to prove this one. So, right. So before that, we see a lemma. Uh, okay. So since m is composite, we take the numbers that are relatively prime to m. So let 1 less than equals to b1, b2, like that up to p of phi m. These are the numbers, be the phi m numbers between 1 and m that are relatively prime to m. So like this, we can enumerate the numbers, right? I name them B1, B2 up to B of 5m because there are 5m numbers, right?
Mhm.
So yes, this part is fine, right?
Phi n is that dash is minus
No, just 5m numbers.
phi n numbers with the phi n numbers between 1 and n that are relative prime to n. Yeah.
Right. So the lemma is so the statement is if GCD of A and M is 1, then the numbers B1A, B2A. So we are product all the numbers with A, B3A, and so on up to B5M of A. So if we take modulo M are the same as the numbers B1, B2, B3 up to B5M modulo M. So if I product all the numbers in this list with A and consider these two separate list of numbers, so as a list of numbers they are same. So they can be in different order. Right?
Okay.
So I think up to
So
this part,
B1
yes.
B1A. What is B1A?
Yes. So this is the list of numbers that we have found out, right? That are relatively prime to M. So B1, B2 up to B5M, right? So
Right.
each number I am multiplying with A. A is the number here. So this A. This A. So we are multiplying
Uh-huh.
each of the number with A. So that's why B1A, B2A. So this is a product. B3A
Right.
up
Mm-hmm.
to B5MA. So if I create this list of numbers and this list of numbers, so these two numbers as a list, they are same. So the ordering can be different.
Okay, they are the same. Okay.
Right. So okay. So let us see how to prove this one. So this will be the main idea. We'll use this lemma to prove the theorem. So the thing is, so suppose, so if B is relatively prime to M, then AB is also relatively prime to M, right? So then GCD of AB with M is also 1, right? Because we know that already A is relatively prime to M.
If B is relative prime to M, right, then AB,
Their
because
product is
B
also
relative prime to M, and A is also relative prime to M, so the multiplication is also
right.
prime. Mm-hmm.
Okay. So the thing is, the numbers, each of the numbers in the first list. So hence each of the numbers in the list B1A, B2A up to B5M of A mod M is congruent to one number in the list B1, B2 up to B5M. So this is true, right? So since the product is also relatively prime, so each of the numbers is relatively prime to M, right?
Uh-huh.
So, but I know that this is the set of numbers that is relatively prime to M. So that is we have found out first. So some number will be congruent to some number here in the list, right?
Okay, so above was they are the same numbers when we
Right.
compare B1A with B1.
No, not exactly. It can be something else. So B1 can be compared with suppose B3. So that we don't know.
Right, in
B1A,
different order.
yes, order can be.
But we said they are the same, but now we're saying they are congruent.
Yes, they are congruent. Yes. So now you have to prove that exactly the same. Till now we have shown congruent. So now we have not show that they are same. So we have to prove that they are same. Right.
Mhm.
So each also we know that each list has 5M numbers, right? So they are so further. There are 5M numbers in each list. Right. So if we can show that that the numbers in the first list are distinct in modulo M, then we are done, right? They are distinct numbers modulo M, then it will follow.
Mm-hmm.
So till now what you have shown is congruent. So if we can show that all the numbers in this first list are distinct, they are not congruent to each other, then since this list also have 5M numbers, this list also have 5M numbers, so as a list they will be same.
Mm-hmm.
So we'll use contradiction that suppose two numbers are congruent in the first list. So suppose we take two numbers, suppose BJA and BKA from the first list, and assume that they are congruent. So what we have is BJA is congruent to BKA in modulo M. Right. So from here we have that M divides BJA minus BKA. So from here I can say that M divides BJ minus BK, right? Since the GCD between A and M is 1.
Right.
Right. But on the other hand, these both numbers BJ and BK, so these are strictly less than M, right? Because that is the collection of numbers that are co-prime to M and less than M, right?
Mm-hmm.
So these numbers are strictly less than M. So this implies this difference bj minus bk, if we take the absolute value, that has to be less than equals to m minus 1, right?
Okay.
Right.
Mm-hmm.
So the thing is, m is a number that divides a number whose absolute value is less than m minus 1. So there is only one option. It has to be 0, right? Other than there is no other choice, right? So this will imply. So the thing is, m divides bj minus bk, and their absolute value is less than equals to m minus 1. So that will only imply that the difference is 0. Other than that, we don't have any other option, right?
The absolute value. But what is the value of n minus 1?
No, m minus 1 we don't need, because m is just a general number, right?
Right.
Fine.
But wait, how did you arrive to bj minus bk equals 0?
Yes. So the thing is, the difference between bj and bk, since both are strictly less than m, that has to be less than equals to m minus 1, right?
Mm-hmm.
So let us see an example. Suppose m is 10, right? So m is 10, and suppose we are saying that some number, so 10 divides some number that is less than 10. So then which numbers? So this the set you have 0, 1, 2 up to 9, right? So if m divides a number that is within this set, the only number that can divide that is 0, right? 10 can only divide 0. Other numbers, it is smaller than 10. It is not possible, right?
N can divide 0?
Yes. Any number can divide 0, right?
I see. You're saying because bj, bk, they are less than n.
Right. The difference must be strictly less than m, right? So that is less than equals to m minus 1.
Because you're saying, okay, n should be a divisor of bj minus bk
Right.
necessarily. That's why then they must be 0.
Right.
Mm-hmm. Okay.
So fine, right?
Mm-hmm.
Yes. So the difference is 0. So this forces bj and bk to be same. But that is a contradiction, because that list is distinct, right? So the
Mm-hmm.
list of numbers what it chose. So this is a distinct list. So this is a contradiction. So contradiction to what? So contradiction to this assumption that suppose we assume the two numbers in the first list are congruent, right? So this
Mm-hmm.
shows that the numbers in the list b1a, b2a, and so on up to b5m of a mod m are all distinct numbers, are all distinct modulo m, right? So
Right.
so as a list they are all same, right? So this first list of numbers and the second list of numbers, they are same. So that is what we wanted to prove, right? So the proof is fine, right?
Right. By contradiction.
Yes. So this proves the lemma. Now let us go back to the theorem. So the thing is, okay, so we showed that if I multiply each number by A, this list of numbers that are relatively prime to M, then as a list of numbers they are same, right? Now if I go back to the proof of the theorem, so let us see. So since as a list they are same, so by lemma, so this B1A, B2A up to B phi M of A modulo M, right? So this is same as B1, B2 up to B phi M. So if we product the numbers, they will be same, right? They will be actually equal, right? So hence the product of the numbers in the first list is actually equal to the product of numbers in the second list. Right?
The product of the numbers in the first list they are the same, yeah. Yeah, they are the
Because
same.
they are just a rearrangement of each other, right? So as a product, the total product will be same. So what I can write is, so B1A times B2A times and so on up to B phi MA. So this is congruent to B1 times B2, so on up to B phi M modulo M, right?
Mhm.
Yes. So now, we can. So how many terms are here? So here there are 5m terms, right?
Yeah.
So the a will be the power of a will be 5 of m. So what we get if we take out power of a from each term? So 5 of m times b1, b2 up to b 5m. So that is equals to b1, b2 up to b 5m.
Mhm.
Right. So we can cancel. We know that each of the term. So each of the term here is relatively prime to m, right?
Mhm.
Relatively prime to m. So I can cancel out these two terms, right?
Yeah.
So if I cancel out these two terms, then I have a power 5m is congruent to 1 mod m.
Mhm.
So this is what we wanted to prove, right? This is the Euler's.
Right. Mhm.
Okay.
Yeah.
Okay. So I think the proof is fine. Okay. So let us see the exercise what they're doing.